Rolling. Oh, it looks like I can, let's see. I'm going to share my slideshow. Do you all see that?
Yep.
Great, great.
Yes.
Okay, I'm usually doing this with two screens. So I've got one, and Zoom is playing ball with me. I can see everything I need to. Well, I see by my watch, it's 1 o'clock. So welcome to our IPS IMMA Digital Human Modeling webinar. We're going to give folks another minute to join the webinar before we begin. All right, we're a minute in, so I'm going to kick off the webinar. Welcome, and thank you for joining us today. Today, Flex Structures and Sandwood Engineering, we're going to be taking you on a trip through the capabilities of IPS IMMA and digital human modeling. Sandwood Engineering represents an organization that's over 130 engineers strong here in North America, based in the United States and Michigan, with offices in Canada and in Mexico. Flex Structures, we're over 50 people worldwide, supporting and developing the IPS, Intelligent Industrial Path Solution suite of software that provides a number of capabilities that we've been discussing over the past few weeks. The presentation today will be joined by, from Sandwood Engineering, John Lukowitz and Owen Janice, to discuss digital human modeling. Myself, I'm Carl Bangert with Flex Structures North America, providing your face on the ground here on this side of the pond. Our focus has been to discuss the transition from physical to virtual validation processes. An example given here by BMW, which has taken its automotive test labs and where the physical prototypes are kept, and really cleared those out in order to do, base their work on virtual validation. So being able to use programs such as IPS cable simulation to determine cable layouts years before start of production. And that's really where the time and money savings comes in with building digital twins, because it ultimately gets you to the goal quicker. So we've been talking the last few weeks really about the physical, the product development side of the vehicle, the cables, the wires, the hoses, but there's human elements as well, and that can also be digitized, and that is through an intelligently moving manikin, IMMA in the case of the IPS cable simulation, that enables you to do advanced studies of assembly procedures, clearance studies, serviceability checks, and more. And with that, I'll hand the microphone over to Owen to take you through some examples using IPS IMMA.
Awesome. Thank you, Carl. So yeah, as Carl said, my name's Owen Janice. I'm with Sandwood Engineering and Ergonomics. I'm an ergonomist under their injury prevention branch. And I'm excited to walk everyone through the capabilities of IPS IMMA. So I'll share my screen here. And before we can get into all the cool tools and start playing around with IMMA, I'd like to kind of walk us through, how we would set up a process to review in the first place. So when we set up a job, for example, in this situation, a damper hook, and its utilization to lift this damper out of this dunnage. So to set up this simulation here, I'll turn my video off here for a second. We're going to start using the path planner within IPS. So to do that, all we have to do is select that hook. Then we'll go ahead and open up our rigid body planning module. And the software will essentially ask us, where do we want to start and end in terms of this process? So very simple. This position here will be our start position. And then I can jump this over to our end position and select set goal. So now the software has noted here the start and end positions. And we're going to go ahead and make sure that the collisions are set up appropriately so that we don't have any collisions with the edge of the dunnage here or the damper as the software figures out how to plan and move this handle assist here into position. So you can see here our static geometry is selected, which is the dunnage itself. But we also have to include the damper because we don't want it to cut through the damper. So we'll go ahead and select add obstacles and OK. And then here you can see AutoBox. This will set constraints in the range at which the object or the handle of the lift assist here can move in this example. So the handle won't exceed the perimeter of this box. And what that really does is allow us to, control the area at which, the task takes place. We don't want this handle going 40 feet in one direction or 40 feet in another. We want to keep it contained to this small area here. Once we have that all set up, I can go ahead and simply click Plan. And the software will begin the calculations to identify the best path possible to complete this task. Depending on the complexity of the geometries involved, so the dunnage or the damper or the hook itself, and obviously the quantity of CAD that's being utilized, these simulations can take a variable amount of time. But generally between 30 seconds to a minute is enough for it to complete these calculations. So we'll just give it a second here, and then we'll go ahead and continue with the study. Perfect. So now you can see the software has planned a path for this hook, essentially from the start position all the way down into the final position without colliding with any objects. And you can see here, rigid body planning successful, path is guaranteed to be collision free. So we can go ahead now and select our motion player. And I can go ahead and play through this motion. So it'll probably play pretty quick initially. I can go ahead and slow that down. And as you can see, the hook is now inserted and scoops up that damper appropriately without colliding with anything. One thing you may notice is at the end of the range here, the line or the path is quite jagged and maybe not as realistic or representative of what we'd see in reality. And IPS has a lot of tools that allow us to modify this path and make it more appropriate for what we would actually see in an assembly or, a workflow process. So all I have to do, again, is go back into here, go into my settings, and add the smooth multiplier and increase that to 20. I can then click OK, and then click Smooth. And the software now will go and identify any of the jagged or very rigid paths within this simulation and try to smooth that out to make it more rounded off and representative of what humans would actually do We're not very jerky when we complete tasks. We're trying to stay nice and smooth. And that's exactly what the software is going to do for us here. So again, as it goes through these calculations, it might take 30 seconds to a minute, but then we'll have a nice smooth path that we'll be able to utilize with our IMMA model. So IMMA is designed to work really, really well with all of the modules within IPS itself. So there's a lot of nice features that make ease of posturing and completing these kinds of tasks a lot more seamless than some other softwares. So you can see now that we have that start and goal session or section. I can go ahead and open up my motion player again and click play. And you'll see now that motion for that handle is much more smooth and much more representative of what we would actually desire for our simulation here. Now that we have that set up, we can go ahead and start to talk about IMMA. So IMMA is the digital human model solution for IPS. And it allows a lot of different functions. We can evaluate reaches, we can evaluate postures, clearances to dunnage, feasibility of different processes like this one here. We can also utilize vision cones to see what the operator would see, as well as trial and example some different tooling changes and engineering controls that we might want to put in place to modify or correct jobs. So to create manikin, we're simply going to go to the Create tab, and then at the very bottom here, we can select Manikin and Family. Now, IPS has a really cool utilization of IMMA here. We can either create a manikin family or a single manikin. The manikin family is essentially a collection of different anthropometries. So we have a 5th female, a 50th female, 95th female. So all kinds of different females from tall to short. And we can also do that with the male mannequins, and they essentially are created as one individual being. So it gives us a really strong capability to evaluate the accessibility of different processes and jobs across a broad range of individuals, not just one individual mannequin. If you do want to create a single mannequin, as we'll start with here, you simply select the single mannequin tab, and then we can select our anthropometric database. So there are 2 databases within IMMA. We can use ANSWER or IFPS. You can then select the sex of the individual that you wish to create, as well as some different parameters of their anthropometry. At the bottom here, you can see we can actually set specific values for their height and weight. So if I wanted someone who's 85 kilograms, for example, and 1800 millimeters tall, we can do that, and the percentile section will update accordingly, or vice versa. You could go in and say you want a 25th percentile individual, and the values for height and weight will scale accordingly. For the instance of this session, I've already gone in and created a manikin, which I'll pull up here. And as you can see, they're giving you a wave. So all of the mannequins are attached by default to a floor, and which you can see in the back here. And as I select the mannequin, you'll see there's this arrow that delineates which floor is attached to that mannequin. Within this floor, we can set different constraints, really to tailor to our usage and what we're looking to accomplish within the software here. So as you can see right now, the X and Y axes are set to infinity. So he can move freely within the scene wherever he wants, but he's not able to translate in the Z axis, as you can see here. So he's not able to go up and down, which would make sense. We don't want him floating or sinking through the floor. But at the same time, we want him to be able to move freely within the environment here. If we wanted to change that, we'd simply go ahead and add in 500 mil. And as you see, when I update this, the floor in the background updates as well. And you can see he's now snapped to the edge of that floor plane. So very, very similar to how we did the box here to set the parameters and the constraints of the hook itself within the damper. We can set constraints within the human here. I can now go ahead and I can move this floor And as you see, when I move the floor, he is updated with it as well. So now that I have it right in front where we want, we can go ahead and begin our posturing for this example. So I'm going to go ahead and set this simulation back to the start. And there are two really good ways to posture mannequins within IPS. So we can do it manually using different points on the body. So for example, here I could manually manipulate his hand and his body position until I got something that I was comfortable with. Or we can utilize something called grip points, which is what we'll do next. So if I wanted to create a grip point, all I would have to do, and I will hide the mannequin here just so we can see it a bit easier, is go ahead and select this hook that we want them to grab. And then I can go ahead and either select here in the create grip point, or I could go create and under the mannequin section, grip point. Now that we've done that, you can see a hand has populated the area where the lift assist is. And we can go ahead and create final manipulations of that posture. Oops. All I have to do is position it into place. And now that I have it somewhere I'm a little more comfortable with, we'll go through this dialog box here. So I'm able to not only select the hand that I want to grab the lift assist with, I can go right or left-handed, but I can also select the posture of the hand itself. So if I wanted, different types of grips, spherical, if I wanted to grab a pinch grip, I could do that as well. But for this situation, we'll go with a cylindrical power grip, just because it's obviously grabbing a cylindrical handle here. So again, I can go and move this hand just to be a little more accurate. And then the drop down here, you'll see manual. I'm able to open and close that grip as I desire. So if I feel like the hand should be a bit more closed and moved a little forward a bit more, I can do that until I have a nice posture that I'm comfortable with. And then I can go ahead and rotate that wrist just so it's a little more natural. Once I have something that I'm happy with, I can go down to the bottom here under grip settings and set different parameters and constraints, very similar to what we've done previously. But for this time, we're going to actually introduce some freedoms for the hand. So as we have it set now with the 0 millimeters of translation, you can see the hand would have to stay absolutely fixed to this point, which again is not very realistic when you're going ahead and doing assemblies. If you think of using a screwdriver or a wrench, you allow your hand to move up and down the handle of that object slightly. So to add in some degrees of freedom here, we're going to go ahead and add 20 millimeters here, as well as some degrees of rotation, just to allow the wrist and the hand to move slightly from the center of that handle. I'm going to add 15 degrees here, and finally 10 degrees here. Once I have my grip point all set up, I can click Done. And now I will bring back my mannequin. One thing that you'll notice, if I take this mannequin and grab their left hand, for example, I currently don't have any collision avoidance set, so they're able to collide their hand through that dunnage in a way that might not be very representative of reality. So if we want to make sure that they don't collide with that object, we simply have to select that mannequin, and then under the drop-down menu, enable collision avoidance. If we do that again, underneath collision avoidance, there's edit obstacles, and we can identify and set different obstacles in the scene that we want them to avoid colliding or clipping through. So we've got that dunnage in place. That's perfect. We're just going to click OK. And we know now when we create this simulation, he won't go through that dunnage. Now, instead of manually posturing all this, now that I have this grip point, it's very, very simple. All I have to do is select it within the hierarchy here and drag it underneath our manikin. Our manikin will now posture to grab and match that grip point that we've created, all while staying within the floor constraints that we've set for him earlier. From this point, I can go back to that simulation that we created earlier, open that up in the motion player, and as this motion takes place, the manikin will follow and complete that task. So I'll run that through a couple more times. And something you'll notice here is that there's actually a collision that occurs with the wrist and the edge of that dunnage. So based off of this handle design being completely vertical, he has to really dip it down quite low to be able to get it underneath one of the spokes in that damper. So as you can see right here, his wrist is actually smashing into the dunnage. And that's why you can see it's offset from where that grip point is. You can also notice in the hierarchy here on the left that there's a line that goes through the hand. And that basically identifies that this posture is not possible with the degrees of freedom that we have set previously. So even though he can translate his hands 20 millimeters and he has that freedom to rotate around that grip point, he's unable to complete this task without a collision. So this was, it would be a really, really good example to, identify, hey, this isn't a job that we'd be able to complete with this tool or this dunnage setup. So a solution to that would be to modify, obviously, the handle to give it a little bit more bend to keep it off of the edge of that dunnage. So that's exactly what we have here, and we'll go ahead and set that example now. So I'll just de-render this handle as well as this manikin. We'll go in, remove that grip point from him. Go ahead and release the grip point. And now I will render a different tool. I'll hide this manikin for a second. And as you can see here, there's a new angle on the edge of that hook. So we're hoping this will help us in completing this assembly and identify, an engineering solution that would allow us to complete this process. So I'll go ahead and turn the manikin back on. And I'll select the grip point that we have here and make some final adjustments with it. Once I have something I'm content with, all I do is grab this grip point and drag it under the manikin, and he will posture accordingly. I can now open up this simulation for this hook. Again, would be the exact same process of what we did previously. And then I can go ahead and play through this simulation. And you'll see he's able to keep his wrist nice and far away from the edge of the dunnage now that we have that bend at the end of the hook. So this would be a successful redesign of this tool. We're also able to do some really, really cool things with the human factors element of the manikin. So what they can see and what their experience would be like when actually running through this process. So to do that, all we're going to do is select the hook itself, and then go over here. You'll see create viewpoint. And now the viewpoint has been populated within the window here. Very similar to the grip points, if I just grab and drag this viewpoint to the manikin, you'll see his head snaps down and is now looking directly at the hook itself. From here, we can go into the individual manikin and open Vision Analyzer. And you'll see here when I add in a new cone, that the cone has now populated the screen, and you can see what he is looking at. And this will update in real time as the simulation goes through. We're also able to open up a window to get his line of sight onto the tool. From this point, we can go back to our simulation, open up our motion player, and then as we play through this simulation, you'll be able to see what he's looking at and then also his point of view and perspective while completing the task. In addition to that, we're also able to, here, let me turn off his vision cone here. We're also able to evaluate static postures within the process here. So if I were to go ahead and open up that same motion player and go back to the start, I can select this mannequin, and underneath the vision analyzer, there's open static evaluation. And what this will do will create a RULA. So a RULA is a rapid upper limb assessment. It's a tool frequently used within ergonomics to assess different postures that are static throughout a task. So you can see now that there's all kinds of scores associated with each of the individual body postures. So the upper arms as well as the trunk and legs. And that'll generate an overall score based off of the posture that you're seeing. If I were to go ahead and run through that simulation and get somewhere like right here, I could then go ahead and say, how is the posture once he's starting to pick up the actual array there, the actual damper there. And you can see that now that I've gone to this posture and reopened up that window, that the group A, group B have been reduced, and by default, or overall, the RULA score has then been reduced as a result. You could then run this through all the way to the end. And then do it one more time. And see the score is now the same here as well. Now this is fantastic for evaluating a single mannequin, but how would we evaluate multiple really becomes the question after this. And as I spoke to before, there's mannequin families within IMMA that really make this really, really easy. So all we're going to do is release the script point and turn off this mannequin. And now we'll go in and we'll open up the mannequin family you can see here. So as you can see, there's two mannequins in this family. There's a 95th male and a 5th female. So we'll know if we can get this task to be completed correctly with these mannequins, that anybody that falls within the range of the heights and lengths of the bodies of these two individuals will be able to complete this job as well. So we're protecting for a range of individuals. The process will be exactly the same as we've done before. So all we're going to do is go ahead and grab this script point and drag this over to our mannequin family. Ooh, so we had a small problem here, but I can quickly correct that. All we have to do is run the simulation. And then set it back. And then I can release the script point, bring it back. There we go. So now we have both of our mannequins postured up with that grip point. And we can run the exact same evaluation we did with the single mannequin. So again, we'll just have to open up the motion player. And as we click play, you can see the difference between the two postures based off of their height, how they would have to complete this task differently from one another. From this point, we could absolutely use the same evaluation toolkit that we did previously. So I could open that static evaluation, and you'll see the different postures between the two individuals. So you'll notice here that the 5th female, since she's shorter, she has to raise her arm up higher in order to grab this hook. And you can notice that here with the score of red for the arm and wrist analysis. Whereas it's not as bad for the male because he's taller, he doesn't have to lift his arm up as high. Now, if we were looking to, reevaluate this dunnage to make it a bit better for the female, while not compromising the male, we could do that simply by modifying the floor that they are standing on. So from this point, I could just click on the floor, raise it up, and now you can see their postures have adjusted accordingly. I could then run the simulation one more time. And see how that changed in floor height. So for example, if I were to put a platform there, how that would impact the job and the postures associated with these two individuals. So if I were to take this and then go into the same static evaluation we looked at before, we can now see that's reduced for both of the individuals there. So we know we've improved this work setup simply by raising the height of the surface they are standing on.
Owen, this has been a great and productive half-hour session. Appreciate you walking us through IMMA and digital human modeling. A couple of quick questions since we are close to the end of our time. So with the assessments that you just did there, does IMMA take into account the mass of objects? Let's say if the mass of the tensioner object were to increase, would that also affect how the manikin reacts?
Yeah, absolutely. So the objects themselves don't have any weight, but the grip points do. So we can go ahead and modify these grip points. So this grip point here, I can select. And under this, you'll see mass as an option. So if I were to go ahead and add a value here, say 10 kilograms, you'll see that their postures adjust as they compensate for that additional load. So we're really able to see, how postures would be impacted by different weights in the hands.
Excellent. And right now, they're not working in tandem, right? We're doing two kind of parallel analyses. By the way, that's an amazing Halloween outfit that you've done mocked up there. But right now they're both working on it individually. Is it possible with IMMA to coordinate tasks to have two separate manikins work on different portions of one model or object?
Absolutely. So for instance, if we were moving this tray and we were lifting it, with two individuals, one on each side, the process would be really the same. We would create grip points on each side. We would have a motion path for this object or this dunnage. And then we would simply create two individual manikins and attach the corresponding grip points to each of them. And then as the motion of that object moved, the humans would follow it throughout. So yes, you can absolutely have multiple manikins lifting the same object, for example, within a scene.
Great. Well, thanks. Thanks very much, Owen. I appreciate you stepping us through this. So we're out of questions and out of time. Could you give us a quick preview? Our final webinar is not a week from today, but in 6 days. And I believe it's going to be run live at Kettering University. Can you give us an update?
That's right, Carl. So we'll be hosting a webinar next Tuesday at 12:30 p.m. At Kettering University, highlighting some of the virtual reality capabilities of the IPS tool and also how those tie into IMMA as well. So it should be a really interesting session.
Great. Well, thank you both for being here, and thank you to our attendees. Look forward to catching up with everyone next week, and appreciate you all stopping in.
Thank you so much.
Take care. Bye now. Have a great rest of the day.